Hello, everyone. Welcome to today's Trustworthy Machine Learning Seminar. I'm glad that you could all make it to today's seminar and our very interesting two talks that we have today, both of them from very well-known names in the interdisciplinary area of machine learning for healthcare, Dr. Katherine Heller and Dr. Jessica Schrouff, both from Google. So, and as many of you might know, the way our seminar is structured is the first hour will be talks and Q&A. Katherine will present first, and then we'll stop for a brief Q&A, after which Jessica will present and we'll do a common question answer after that. And during the talk, please feel free to present your questions in the common chat or upvote others' questions as well. After 1 o'clock, we're going to take a little bit of break and then roll into our participant-driven discussion. The first hour will be recorded. So if you do not want yourself to be recorded, if you do not want to appear in the recording, you can tune out now and watch the video on YouTube and then join us for the second hour for the non-recorded version, in which we'll have a more free-form discussion among all participants. A little bit about our initiative. Many of you are familiar with us by now. We are a group of 8 people right now, and this really started off as a group discussion of things centered around how we can kind of pull together the community that has a common goal of building solutions towards trustworthy machine learning methodology. And we are glad that we are here, almost 1 year old, and we have kind of succeeded in building an approach towards bringing this community together and forming meaningful conversations. Our current goals and efforts include not only the seminar series, but also a list of resources in our website that includes tutorials, papers, and courses for people who are interested in diving deeper at different levels of the theory and practice of trustworthy machine learning. We have an active Twitter handle through which we propagate recent news and publicize recent works of researchers as well. And also we have a number of activities coming up later in the year for which stay tuned, which involves a symposium and other activities as well. Coming back to today's agenda, as I mentioned, it will be talks, the talks by our 2 speakers for the first 40 to 45 minutes, after which we'll take a Q&A, and in the middle we'll also stop for a Q&A. And after the first hour, there is a break and then the participant-driven discussion. Going to our stars of today, our speakers, I'll introduce Katherine and Jessica briefly and then hand it over to them. Both of them do research in the interdisciplinary area of machine learning and healthcare. Dr. Katherine Heller, our first speaker, is a research scientist in Google Brain. Before joining Google, she has been a faculty at Duke University, and her background, research background, educational background is from Stony Brook, Columbia, and a PhD in machine learning from UCL. She has been a recipient of multiple awards, for example, the NSF Postdoc Fellow in Google Brain. And we're really glad to have Katherine here, who is a really well-known name in this area and has done substantial research in bringing together these 2 disparate fields and devising solutions that are really implementable. Our second speaker, Jessica Schrouff. Dr. Jessica Schrouff is also a research scientist at Google Research, and her research methodology is focused on the same domain as well, machine learning for healthcare. She is also looking into the different aspects of trustworthy machine learning that are relevant in the field, for example, fairness and interpretability, and how they play out in different aspects of healthcare related solutions. Dr. Schrouff is also actively involved in diversity, equity, and inclusion initiatives such as the WIML group, Women in Machine Learning group, and she is also the founder of the Women in Neuroscience repository. So with that, I'll hand over to our first speaker, Katherine. Katherine, the floor is yours.
Thanks. I really appreciate it. Okay, let me start sharing my presentation. All right, and we are talking today about integrating predictions from electronic health record data. And specifically, I am going to talk about some of our work on sepsis, which is work that was done at Duke University Hospital. It was actually while I was a faculty member at Duke. And we worked with people. We had a big team of collaboration between people who did computational work in the stats department, and then also people who were in practice at Duke University Hospital, infectious disease specialists, and then people at the Duke Institute for Health Innovation who were responsible for getting innovation into the hospital setting. And so, okay, let me start with sepsis. What is sepsis? Sepsis is a life-threatening complication from infection. It's usually a hospital-acquired life-threatening complication from infection. So you often get sepsis because it is an infection that you get from, say, like the insertion of a central line. There are a lot of new sepsis cases, so over 750,000 new sepsis cases in the US each year, and these cases have a very high mortality rate associated with them. So the estimate is 30 to 50%. Hospitals are very incentivized to work on sepsis as an issue because it's usually hospital acquired, and because they get dinged by centrally by the U.S. government if they don't reduce their number of sepsis cases. So I should preface this by saying the reason we started working on sepsis was because we had started working on other things first, like chronic kidney disease with nephrology at Duke. And it was something that we couldn't really get hospital leadership excited enough about in order to justify funding AI and machine learning. And we couldn't get them excited enough about it because it was unclear how reimbursement was working for nephrology in general. And I think that's true of a lot of diseases in the hospital setting. So you tend to see people in AI and machine learning working on a very similar set of diseases. And I can tell you this is why. There are a certain number of things that hospitals, at least in the US, know that they are going to get dinged for centrally. And those are the things that they really care about. And those are the things that will probably lead to integration of AI technology in hospitals first, because it's clear how reimbursement is working. Anyway, so sepsis is one of these things. We started working on sepsis. What they were using at the time was called the NEW score. This is a score that has been more successful in other places. So I think it's more successful in the UK than it is in the US for reasons that are not clear to people. And the way that the score works is shown in the lower right-hand corner, right? So there are a number of vitals like respiration rate, O2 saturation level, systolic blood pressure, etc. And there are a number on the rows, and then there are a number of points on the columns. And you get 0 points if you're in the normal range for that particular vital. But if you're either too high or too low, you get some number of points, and then you just sum across the rows. And that's your overall score. And if your overall score is higher than a certain amount, like 6 points, right, then the news warning system alerts that you are at risk of decompensation. And so again, this is an effective rule of thumb in many instances. You can see that there are some weirdnesses about the score. So for example, if you have a systolic blood pressure of 219, you're totally fine. But if you have a systolic blood pressure of 220, oh my gosh, you're probably dying, and you have 3 points added to your score, right? And so there are a bunch of kind of fickle things like that. And we looked at the score, and we were like, okay, we think we can probably do better with some more modern machine learning techniques. I should also say that the score, one of the reasons why it wasn't particularly useful at Duke University Hospital, and in fact, they stopped using it entirely, is because it false alarms so much. And it was false alarming enough that nurses were basically ignoring it. And so that was something that we were very conscious of when it came to designing our own system. We didn't want something that was going to false alarm so much that people were going to start ignoring it. Okay, so what is our problem? Our problem is that we want a system that's going to detect whether or not it thinks that you're likely to have a sepsis infection. But in order to do that, it has to generalize off of a bunch of labs and vitals, which are measured at very irregular times. So for example, here we see that this is the data rate for a single patient in their hospital stay. So the time in their hospital stay can be seen going from left to right on the x-axis, and then all of the labs and vitals are given on the y-axis, and you can see what those are. And so you can see very clearly when certain things happen. So for example, in the box is this patient being transferred into the ICU. When they're in the ICU, things are measured much more frequently than they are on the floor. And you can see that reflected in the rate of data collection. So we want to be able to take in this irregularly sampled time series data, and we want to be able to have this kind of binary prediction coming out at the other end about whether or not we think the person is septic. And so if we think about it just sort of very crudely, like if we want to predict whether or not we think somebody's likely to be septic, we kind of want a binary classifier at the end of the day. But since this is time series data, we need something that's going to smooth out the irregular time sampling, so that we can feed regular data into our binary classifier. And that's what we got when we put a Gaussian process together, so we could estimate values at regular intervals, even if they were irregularly sampled, together with a recurrent neural net binary classifier, which works over time. And that's what we did. So we had a multivariate Gaussian process recurrent neural net model. We were able to learn the parameters of this model in an end-to-end fashion. We were able to employ some tricks in order to speed it up. So like the reparameterization trick of Kingman and Welling, where you're exchanging the gradient and the expectation. And then other things like looking at measuring the expectation with how many samples. So a lot of times people, when they do work this way, look at even a single sample for estimating an expectation. We found that actually the uncertainty here was higher, probably because the data is more limited, and we did much better when we took some form of uncertainty into account by, say, looking at 10 samples. And so I guess that's like the first thing I want to say is that uncertainty can be very important in these settings, and it's important to take it into account, particularly when we're not in an extremely high data setting. But anyway, we were able to employ a bunch of these tricks, and we were able to learn end-to-end this multivariate Gaussian process recurrent neural net classifier in a short period of time. We also changed the multivariate Gaussian process so that it took into account certain things in our setting which were important. So for example, when we look at the mean of the Gaussian process, we think about like, okay, somebody could not have a high fever, but they could not have a high fever because they're not sick, or they could not have a high fever because they were given a fever reducer recently. And so there are certain reasons why you might see certain labs and vitals come out. And this could correspond to them having been given certain medications recently. And we want to be able to take that into account. So when we look at the mean function of our Gaussian process, we look at the time interval between now and when the last time was that they were given a medication of a certain type. We also look at smoothing. So we can smooth out over time in order to have reasonable estimates of labs and vitals, even when we're estimating them for a particular time interval. But we can also smooth out over patients so that even if we don't see a particular lab or vital for a particular patient, we can still come up with an estimated value of it by smoothing out over patients that look like this particular patient. Okay, so we incorporate that into our multivariate Gaussian process, RNN. And we come up with a model that we can deploy. And this is a particular case of a particular patient who came into Duke University Hospital, and I will go through their case of like what our how our prediction method worked for them. Okay, so on the top you see the risk in the dark line. That's the risk score that our multivariate gassing process RNN is giving for this person being septic. And then below that in blue, you see various labs and vitals. Those are given by the dots in terms of where they're measured, and then the blue line is an interpolation between them. The blue dot on the top plot, the big blue dot, represents the administration of antibiotics to a particular patient, to the patient. And then the x-axis is time, and the y-axis is the things that I just mentioned. So here, this particular patient is coming into Duke University Hospital in order to have pulmonary surgery. So they have a lung problem, and that lung problem can hopefully be resolved by surgery. And as is standard, in the run-up to surgery, the patient is given antibiotics, and you can see that happening in the top plot. And then at the Red Cross, the patient has the surgery, the pulmonary surgery that they were scheduled to have. And you can see almost immediately the patient starts decompensating. And you can see this if you look at their temperature rises, their pulse rises, their oxygen saturation level goes down. And at the Yellow Cross, the patient is admitted to the ICU. So there's a problem. We don't yet know what the problem is, but we know there's a problem. We know they're decompensating. We're admitting them to the ICU. So at this point in time, if you're looking at the black line, which is the prediction that our system is making, you can notice that it thinks that it's highly likely that this patient is at risk for being a sepsis patient. And then we measure their lactate, which is a direct reflection basically of how likely it is that this person is septic. They continue to decompensate. Their lactate score comes back high. And at this point, our algorithm just thinks it's incredibly likely that this is a sepsis patient. And eventually, the doctors start administering the patient more antibiotics to treat the infection. And the person is eventually diagnosed as having sepsis at the vertical red line. And they're given more antibiotics, and then at the purple cross, the infection is found through culture. And so what we like to point out here is that there's an incredible amount of time between when our algorithm thinks that this is likely to be a sepsis patient and when clinicians start administering antibiotics to the patient. There's 36 hours between when our algorithm thinks that this is likely to be a sepsis patient and when they're actually diagnosed with being septic. But even like clinicians can suspect that this person might have something and start treating it ahead of time, and that's what you think might be reflected in the administration of antibiotics. But there's still a 17-hour time gap. So whether you're looking at 17 hours or 36 hours, that is an incredibly long time in the life of a sepsis patient and can really influence mortality rates potentially. Okay, so going off of an example of more than one patient, right? We looked at 52,000 inpatient encounters in terms of training our model. This is all the data at Duke University Hospital over 18 months. And then we looked at the subsequent 14,000 inpatient encounters over the next 6 months for testing. We used 31 longitudinal variables, so 6 vitals, 25 labs, baseline covariates, medication classes that have been grouped by clinicians, et cetera. And what we found, and then you will see, you can find plots comparing more things than the AURs or C curve that I show on the left. But what we found very consistently was that our multivariate gassing process RNN model outperformed all of the other competitors. So whether this was a plain RNN, logistic regression, or the new score that I showed you earlier, we were pretty consistently doing better. And then, like I said at the beginning, we were very conscious about the false alarm rate because we didn't want the false alarm rate to be too high for the nursing staff. And we knew that the new score had that problem. So we worked with our clinical collaborators in order to find like a good place on this ROC curve where our accuracy could be high, but we still weren't false alerting so much that the nursing staff was going to start ignoring it. And we basically found a place where we had one true alarm per one false alarm is what we ended up with. And we created, the team created an app that the staff this was deployed to the emergency department at Duke University Hospital, and basically an app that a web app that people could use, rapid response team nurses could use in order to monitor every single person who was admitted to the emergency department at Duke University Hospital. And the way this looks is kind of what you see in front of you. This is obviously not real data because that would be a massive HIPAA violation. But like a patient comes into the emergency department, you know, their demographic information like their name and age, etc. And then you know what kind of prediction our algorithm is giving in terms of the likelihood that this patient is septic. So you get that in the triage stage. And then in the monitor stage, there are various things that you can do if you think that the patient is likely to be at risk for sepsis. So you could do additional chart review or call a doctor or nurse. And then if you basically think that it's highly likely or the person is diagnosable in terms of having sepsis, you can start treating them. And there are these things mandated by the US government called treatment bundles. So if you diagnose somebody with sepsis, you have to have a particular treatment regimen that you follow with them, right? So like every 3 hours, you have to be giving them IV fluids. Every 6 hours, you have to be giving them vasopressors. And you would think that hospitals would be very good at abiding by these treatment bundles, but it turns out they're not really. And so Duke University Hospital's previous rate for compliance with this treatment bundle was about 50%. And one of the reasons that we were interested in Sepsis Watch was because one of the things that it can do is remind nurses and doctors to stay compliant with this treatment bundle, so people are getting treatment when they should be. And we were able to, for patients who we suspected of being septic, raise treatment bundle compliance by about 6%, and for people who are diagnosed with sepsis, over 10%. And you see that here. Okay, so then another thing that was done after we had built this system, we deployed it to the emergency department of Duke University Hospital. We have Sepsis Watch. It's being used by nurses and doctors and getting used on all of the patients who come in, and that's great. But then we had people follow up and look at the social implications of what we've done. And this is work really by Madeline Elish, who came in and looked at all of the social implications and did an ethnographic study. And she interviewed lots of people, particularly the rapid response team nurses that were working and seeing the results of Sepsis Watch. And what she found was that in terms of workflow in the hospital, the sort of everyday norms were very deeply destabilized and disrupted in ways that we hadn't properly anticipated. And even more surprising was how the destabilizations and disruptions were repaired. And trust and accountability were basically regained through methods, and they weren't automatic methods. So they weren't interpretability methods. They were really social things that were happening in the emergency department. And so Sepsis Watch and the incorporation of the Sepsis Watch system disrupted the way that power hierarchies have typically worked within a hospital setting, right? So, sorry. So basically, hierarchically, it's that, like, infectious disease doctors in the hospital setting have medical judgment about somebody being septic, and now we have this automated system, and the automated system is being used by RRT nurses, and they've got to convey the information coming in off of the system to a doctor who might be to some degree reluctant to hear this, right? Because it's kind of like a nurse, an RT nurse, giving you feedback about what your diagnosis might be. So they talked about their experience, the RT nurses, their experience working with doctors who just don't like having their medical judgment questioned. So that was something that they had to work to overcome. And so then they talked about like picking up the phone and like all of the preliminary conversation about like them asking like how they were feeling and how things were going that day and whatever, so that they could have an indication of how the call was going to go, where they were telling them what the automated system was saying. So there's a part of this that involves emotional labor on the part of some of these RT nurses. And lastly, they did extra chart reviews. So the automated system could be giving a particular diagnosis, and the RT nurses go look for extra evidence from the chart to back up what the automated system is saying. So this is like extra work that they're putting in terms of like chart review. And basically, like the overall finding was that the repair work being performed by the RT nurses could be effective and empowering, but in part because their expertise was being supported and not undermined by the team that was working on Sepsis Watch. And the team is broad, right? Like this it includes computational people, but it also includes a lot of like doctors and nurses who were involved in the design of Sepsis Watch, and everybody being on board with having the system there and being run on the patients coming into the emergency department. So this is really my plug for large collaborations involving computational people, involving clinicians, both doctors and nurses, involving social scientists. All of these people need to get together in order to develop an effective system. Okay. And yeah, that would be my take on like trustworthy ML. How do we make things more trustworthy? We need the right collaboration in order to have all the key players involved. And so now I'll pass it off to Jess.
Thanks a lot, Katherine, for the very insightful presentation on how exactly to embed very technical methods to extract very meaningful insights, and specifically in such a challenging technical setup and a real life situation. So any questions from the audience at this point to Katherine? I don't see any questions in the comments section right now. So let's move on to Jessica's section for now, and we'll get back to the question answers after in the final 5 or 10 minutes. Okay, so actually there is, sorry, Katherine, there is a question actually from Sahil, which says that it's not a technical question, but he's asking that how did you get to know about the problem? So I guess some question about the scoping phase and how that worked.
Oh, yeah. I mean, so to some degree, it's just what I said before, which is like we tried actually working on other stuff, and we found that the hospital incentives were aligned on this particular problem. And to some degree, we got that feedback from hospital administration, and there were doctors who were interested in working on it. But like doctors are interested in incorporating this kind of technology into the diseases that they work on is something that we generally found, right? So like looking at sort of, especially in the beginning of incorporating AI into medicine, right? Like looking at what it is that's going to convince the business end of hospitals in order to try to start investing in this technology.
Got it. Thanks, Katherine, for clarifying that, the motivation of the project and how it began. So with that, I'll hand it over to Jessica for the second half of today's seminar. Jessica, the floor is yours.
Thanks, Subho. Thanks for having me. So I'm going to follow up on what Kat has presented. I'm actually going to talk about interpretability. And I'll give another example of what we can predict with electronic health records. I'm going to focus on another type of acute patient deterioration, which is acute kidney injury. And in this case, acute kidney injury is basically a failure of your kidneys. It affects 1 in 5 people that are admitted to the hospital, and it can have severe consequences where you have to be on dialysis or even death. Now, the damage can be reverted if it's taken early enough, and that's where early prediction of kidney injury is then interesting. Now, in terms of the data, we were dealing with slightly different data. So we have diagnosis, medication observations sampled irregularly, like Kat was saying. In this case, we don't filter for like a small list. We actually take the whole thing. So it means that we have a lot of variables. We bucket things into 6 hours. And so we predict every 6 hours, we take the whole history, and then we predict the risk of AKI. And we predict within a certain time horizon. The scope focuses on the next 48 hours because that was the most clinically useful window. But actually, there were different horizons that are reported and that are as actually different heads into the model. So one thing to note about our data representation is that in terms of the missingness, instead of doing data imputation or other type of handling the missingness within the model, we actually explicitly represent it. So we have for each vital or lab, for example, they have a numerical value when they're present, but otherwise 0 wouldn't necessarily mean anything. So in this case, we have an additional binary variable that says whether the lab or the vital was sampled or not. And then we have the actual value for it. So it increases our feature space even more. So in terms of the model architecture, so we have a stacked recurrent neural network that takes in the time series. And then we have the main targets, which are these different time horizons from like 6-hour predictions to like 72-hour predictions. And we also have auxiliary targets. These were created, and there are labs that are and other features that are directly related to the diagnosis of AKI. So for example, we have creatinine, which is a protein in your blood that indicates kidney damage, like kidney function. And we are predicting this as a continuous value along with the targets as well. Now, in terms of the results on Veterans Affairs data, so this is a quite large data set. We see that ROC-AUC is 0.92 and PRAUC is 0.3. These are better than non-recurrent neural net baselines. There are no transformer comparisons. The main reason for that is the size. We have over 600,000 features in that model. We have also replicated these results. We have used the same architecture on Mimic3, where we have slightly different numbers. They're not directly comparable because Mimic3 is intensive care unit and VA data is on the floor. So they're not, like the prevalence is a bit different. But what we can see here is a result for a single patient where we have this like creatinine, so this protein I was mentioning, and that gives the actual AKI label for outside of the model. And so we see that over time, creatinine is increasing, and then the patient is diagnosed as an AKI according to the clinical label, a bit like the news label that Kat was mentioning for sepsis. While the model is actually able to predict a bit over 48 hours in advance that the patient is at risk for AKI. Now, this all sounds really promising, but it's also very important to understand what the limitations of the model are. try to understand what it's actually learning, and then how we could communicate these learnings and these limitations to clinicians so that they can use the tool or the model in a very safe way. And not only at the model level, but also at every single prediction, how can they, like trust, but also be skeptical when needed for each prediction of the model. And we actually turned to explainability for that. There are different techniques we could have been using, but we tried interpretability. And we have opened a big Pandora box that I'm going to unpack a little bit. So just to recap some of the challenges with EHR. So it's temporal, there's missing data. And also another factor is that it's heterogeneous. So you have binary variables, you have numerical variables, discrete and ordinal variables. They're typically one-hot encoded, but especially these variables, they have different distributions and different healthy ranges. So earlier in one of the plots that Kat showed, you had oxygen saturation, and the healthy range for that is actually very close to the maximum range, which is like 100%. And there are very few points outside of that range, actually. And you can have 100% if you're mechanically ventilated as well. So we can see that there is like this disparate effect of the healthy range that we're discussing, and the correlations with the other features, of course. And then when we think about interpretability, then here we have semantic features. So it's actually like each feature represents something we know. It's not like a pixel in an image. So that's actually helpful. But we have 600,000 of them. So what do we do with that huge list? How does the choices we make in data representation, how do they affect the explanations, and how do the different characteristics of like missingness, heterogeneity, how do they also affect our explanations? And then once, assuming we have a very faithful list that we somehow have thresholded, is this really understandable? Can the clinician take action, or like be skeptical or trustful towards a prediction based on that list? So what we did is we took the AKI model on Mimic, and we applied two very popular methods for post hoc attribution. The first one is occlusion, where for each time step and each feature present at that time step, you remove it. And removing actually has a meaning. So typically for an image, you would like set the pixel to 0. But that 0 is actually a baseline. And if your variable doesn't have 0 in its range, it's not going to mean anything. If you're doing standardization, 0 would actually mean the average across the training population. But now if you're using unit range as a normalization, 0 is actually the lowest value that you're observing. And this value can be a very unhealthy value. So again, we see that the baseline is actually could be a strong hypothesis, and that this hypothesis might vary based on which feature we're looking at. So it's already not a very easy problem once you start looking deep into it. The other method is gradients that doesn't have a baseline. And we're looking at global explanations by aggregating across all patients and time steps. Again, there are many ways of aggregation, but it's just a absolute value average. So the first thing we're looking at is global results, arbitrary thresholded at top 15 for occlusion for gradients. And what we see is that first thing, we have two different methods, and we actually have two fairly different lists. It's not that surprising, but there's very little overlap. Maybe the main overlap is serum creatinine, which is reassuring because we're expecting to see creatinine, but at the same time, it's still not super helpful that they're very different. The second thing is that if we look at the thresholding for occlusion, there's actually no clear cut, and we don't really know where to stop. For gradients, it might be the first one where you would have only one feature, which is probably not very helpful. Another thing that's interesting is that it seems that the model and if we focus on occlusion and we assume that occlusion is right, that the model is looking more at the binary variables. So when we say that there's a sample of something, rather than at the value of that sample. And if we think about some of the tests, that can be a bit surprising, especially some of them are part of like routine tests. And so we were wondering whether it's really purely an effect of the model looking a bit over the clinician's shoulder, where they're looking at what the clinicians are doing in terms of the sampling, or whether it's also maybe a numerical factor. And what we did is we took some synthetic data, and we had binary features and numerical features, and they had a ranking in terms of their signal-to-noise ratio, but they had the same amount of information in binary and in numerical. And what we saw was that by switching a couple of things, we could have the model rely more on the binary variables independently of their ranking, or on the numerical variables. And so we're wondering here, basically by doing that extra analysis, is if it's not like a mix of different factors, including like some of those numerical factors, where it might just be that binary variables are just cleaner in terms of signal-to-noise ratio for the model to rely on, rather than the model really looking over the clinician's shoulder. Like another thing to look at in purple are these different variables. And if we think about acute kidney injury, then dialysis is something that really makes sense. The bear hugger is like a blanket that keeps your body temperature constant, and it's when people are really sick. And we see that overall, these seem like just indicators that patients are really sick, and potentially more like consequences of patients getting really sick, rather than the causes of AKI. And for causes of AKI, then in bold, this one is interesting actually, because this is an antibiotic, and sepsis has been determined as a potential cause for AKI. And so we're going to follow antibiotics in the following slides as well. And now lastly, in orange, we have these variables in the top 15, and we're not really sure what they're there. And as an anecdote, actually during the development of like a follow-up study where we looked at the generalization of the architecture on mortality and length of stay, we actually submitted the list of occlusion scores to clinicians for their review to see if they made sense. And there was a bug in the code. And we didn't actually give a list of features ranked by their occlusion scores, but it was more a random list of features. And on that list, it was whether the patients were wearing glasses. And everyone was actually trying really hard to make sense of why people wearing glasses would be more at risk of staying longer in the hospital or dying in the hospital. And so that really shows that here, like, there can be a high confirmation bias that's very important to look at. And I think another factor is that these scores are just given as they are. For predictions, uncertainty is becoming fairly common. There's a lot of work around that. But for attributions, actually, it's quite rare to see confidence intervals or uncertainty. And I think this is probably something that would be more interesting to dig in. Now, in terms of the local results, this is selected for a patient that received antibiotics. So again, the list top 10 is fairly different. Again, there are things that make sense in both, but it's very hard to actually say what makes most sense. In black, we have that antibiotic that I was mentioning. But again, if we think about, as a clinician, you're just given that list. Let's say one of them is right. Can you really look at this list and see, well, it's probably because the patient is having an infection that might turn into sepsis, or that is already sepsis. And so in this case, we thought a bit more in terms of what we're trying to do. And these different causes of AKI, they are more like clinical concepts than a single feature. And so we relied on testing with concept activation vector, and we applied that to EHR to see if we could actually transfer the concepts into EHR. And so TCAV works by looking at the encoding of the concept into the network's activation space. So if you have images that are red and images that are green, and we're looking at the color concept, and you pass them each through the network, you record the activations, and very conveniently, we have a two-dimensional layer here. And based on this activation, you train a linear classifier, and the normal to that classifier is basically your concept activation vector. So your concept as encoded by your network. And for a new sample, what you do is you look at whether the gradients for that new sample align with that concept. So whether if you move into the direction of the concept, this would increase your prediction. And we're doing that for antibiotics. So we have for concept patients that do not have AKI, they get antibiotics, and then they get AKI. And then for control, we have patients do not have AKI, and then they develop AKI. So we're trying to look at the differential effect of antibiotics on AKI. This is not a causal relationship. This is just something purely relational, but at least we have this like time series of events. And what we see is that we have some global metrics where we can look at whether the concept is present or not in the activations. So when the patients receive an antibiotic, which is here in purple, closer to the AKI, their score seems to be higher. So they seem to be more encoding of that antibiotic, which is not as much when they are further away from the event. And also, when they don't get an antibiotic, that score is lower as well. On the other hand, if we look at the alignment with the gradients, we see that overall, if we move in the direction of antibiotics, we're going to have an increase in the prediction, so an increase in the risk of getting an AKI. And that metric doesn't make a difference when the concept is present or not in a sample. And now at the local level, if we look at a patient that comes in with no AKI, gets antibiotics, which is this gray line, and then gets AKI, the yellow line, and the model is correctly predicting that the patient is going to get AKI, although not exactly at the 48 hours mark. We see that over time, the activations align more with the antibiotics concept as well. We looked at another concept, which is self-reported sex, to see if the model was biased. We were not able to build a significant CAV. It's interesting that the model was equally performant on females and males. Now, this is definitely a negative result and should not be interpreted as the model is not biased. So in conclusion, for this part, because I think actually the conclusion to CAT should be the conclusion to overall talk. But I guess the more I work with explanations, the more difficult I find to trust them, because they depend on factors like which data representation, which normalization. I haven't talked about prevalence, but that actually also plays a role. And you need to really get into the nitty-gritty of what every single number represents and how it is treated to start and understand why an explanation would change one way or another. And I guess it's more of a warning that applying a method, an interpretability method a bit blindly because it's popular can be very misleading. We also saw that the confirmation bias can be high and that human-grounded evaluations are necessary. Typically, they're done by comparing the prediction without attribution with the prediction with attribution. I would also argue that we need a third option, which is the prediction with randomized attributions. And for future work on this specific TCAV direction, we're looking at other architectures because we're not married to RNNs. Causality and generating counterfactuals would be really interesting. And then clinical evaluation is probably like the most important part to see if this is actually useful. There's open source code in case anyone is interested. None of this work would be possible without our team and collaborators. So thank you to all of them, and they're not all on the slide. And thank you for your attention.
Thanks a lot, Jessica. It was really enlightening to learn about not only the model itself, but the interpretability aspects and the challenges associated with them. So we have one question from Sahil Verma. And Sahil, you can actually unmute yourself and ask the question yourself if you'd like to.
Oh, wow. Hello.
Yeah, we can hear you.
Oh, yeah. Hello. Hello, Jessica. Thanks for this talk. I had a question about the feature attribution explanation method. You used occlusion and gradients as the explanation method for feature attribution. I was under the impression that the most popular techniques for feature attributions were Lime and SHAP, which, but you didn't choose to use them and choose two different. So I was wondering if you had some specific reasons for that.
Yeah, thanks, Sahil. Yeah, so the dimensionality of the problem is really limiting what we can do with like the 600,000 features. There's also like the fact that in terms of any kind of distillation methods where you would try and approximate your predictions with another model that's actually more transparent, I do have reservations for that because I've seen it used where you approximate your predictions and then you use that simple model that is transparent to make new predictions. And I think that this makes sense. But in our case, we would have been using the more complex model. And there are a lot of different ways you could approximate your predictions for a given model. So I guess we would not be sure of the uniqueness of the transparent model that we obtain, and that was my reservation for trying those methods out. We tried integrated gradients as well. We tried temporal integrated gradients, which we found was actually a little better at not being so affected by normalization strategy or prevalence, but they're more computationally expensive as well.
Okay, thank you.
So our second question is from Benjamin Pikus. Benjamin, you can unmute yourself and ask the question.
Hi, first off, thank you both for this really insightful talks. I think really interesting and very cool work that you're both doing. I just have a kind of quick, perhaps trivial question. I was wondering if there's kind of a defined either metric or definition for, your choice of like explainability or interpretability or kind of whichever word you want to use for like human prediction. So evaluating, let's say like doctors' decisions when deciding like sepsis or AKI.
I think that's a great question. I think it's really hard to ask clinicians what their reasoning is. I guess the way for human grounded evaluations, I guess I have envisioned them as mostly like seeing whether the clinician is getting better at predicting the events with attributions compared to without. It would be interesting. I'm sure there is work that's doing that with like explanations given by someone else and seeing if they're better at, predicting something. Kat, do you have any insights on that?
Yeah, I mean, not really, but so I know that in the Duke sepsis case, they're in the process of studying that, right? Like, what is the actual effect on mortality rate of having this extra prediction? And that's jury's still out on that a bit. But like I said, I could present like certainly like non-ML like sepsis bundle stuff, and it was very clear that was having a lot of impact right away. And Yeah, that's right. Jess is right. You would need studies, and I think we need a lot more studies showing what the impact is on the workflow of people in a clinical setting, right? When we introduce these models to them. And then, like, even if it isn't immediately good, right? This is something that I discuss a lot of times with people, right? Even if it isn't immediately good, is that really a problem of like the prediction algorithm, or is it a problem in that we haven't like really worked out workflow integration of the system yet, right? Because it could be that we're just like, again, failing at a social level to get like the system properly integrated into how the workflow is going, and there could be negative repercussions kind of coming from that. That's negatively affecting sort of like correct diagnosis or mortality rates, whereas it doesn't necessarily need to be that way, and it's not necessarily for algorithmic reasons.
Gotcha. Thank you so much. That was great. Thank you.
Thanks for the insights, Jessica and Katherine, to both of you. So we have like 1 minute left, so I'll wrap up with just one question to both of you, which I think might give useful insights, considering that our audience, many of the people in our audience in this seminar maybe, and also of Trustworthy ML in general, are early career students or postdocs or other researchers. Is that so both of you are in Google doing research in an industrial setting. So I was wondering that if you could give some sort of insights regarding how does industry research, how does that differ from an academic style research? And not only that, but also some kind of idea regarding how do you balance these two different priorities of research versus profit generation for a specific business. So that aspect, I was wondering if you could give a little bit of insight.
I mean, I can take a stab at an answer to that. I mean, I think that Google has fallen very rightly under a lot of criticism recently for, the insertion of corporate profit values sort of into research, and I think it's something that we have to stay really vigilant about, right? You do have that concern, but you have that concern even at an academic level, right? You're a part of an academic institution, and that academic institution, though it's less than a company, right, and doesn't have quite the profit incentive, will try to insert its like institutional values on all of its employees as a researcher. And you see this come up particularly in cases of like sexual harassment and things like that go on at academic institutions as well as in industrial settings like Google. But I think that there's always this tension, and we are researchers, and we really try to sort of think about research first and foremost, and its impacts on the world first and foremost, and about institutional values later.
Thanks for the insights. It's really helpful to kind of put that idea in front of, let people know who are maybe thinking about joining an industry lab or trying to do that trade-off, that okay, what are the factors involved in making the decision, and how do things work? So yeah, thanks for the straight talk, if I may say so. All right, so since we are at the top of the hour, I'm not going to restrict our speakers to stay for much longer. Katherine, Jessica, thanks a lot for joining us today. And I think we had a really great session regarding one of the lesser known topics that we have explored until now, which is machine learning and healthcare. And you also wove in different aspects of trustworthiness and interpretability into it. So thank you so much for joining us. And as you know, the second half is a social. You're welcome to stay in it, but it's totally optional for you. So yeah, with that, thanks a lot.
Thank you so much for having us.
Thank you.